Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 17, Simulating Production Scenarios. What if you could test every production decision before making it? In this episode, we explore how manufacturers use digital twins to simulate different production setups, from shift patterns to line layouts, and choose the best option without risking a single real-world interruption. You'll hear how DBR77 helps companies compare KPIs across variants, reduce cycle times, and optimize costs through intelligent, scenario-based planning. No more guesswork, just data-driven choices. Factory on Air is powered by DBR77, the platform that helps you plan, simulate, and continuously improve, one scenario at a time. Let's begin.
If you're running, say, a modern manufacturing plant or maybe a complex logistics center, you know this headache. It's this core, almost existential problem you face, well, every single day. The market demands flexibility, fluidity, right? But your physical assets, your factory floor, your warehouse layout, they're fundamentally fixed. Orders change, sometimes weekly. Your supply chain materials can fluctuate wildly, unpredictably. And staffing, that shifts based on, dozens of factors. Yeah. So you constantly feel this pressure to reorganize your production flow. But the risk of a major operational failure is just massive. Just think about it for a second. How do you confidently switch your factory from, say, a 3-shift model down to 2? Or radically change the sequence of 4 absolutely critical operational stations? How do you do that without basically hitting the pause button on actual production for maybe a month while you figure it out, while you test it? The truth is, you can't. The cost, the sheer risk of lost volume, the complexity, it's all just too high for that kind of real-world trial and error experimentation. Okay, let's unpack this. Our deep dive today, it's focused entirely on production simulation. This is really the essential tool that lets you move that operational risk off the factory floor and, well, into the digital realm. We're going to really analyze the mechanics of how companies are testing dozens, sometimes hundreds, of alternative scenarios, how they select the mathematically optimal solution before they spend a dime of capital or risk any major disruption. And we'll be looking specifically at the DBR77 platform and its digital twin technology as the engine that makes this all possible.
It's crucial to grasp the sheer speed, the velocity at which the industrial environment is changing right now. This old idea that a company can just establish a single static arrangement for production and then, coast for years, that's completely obsolete. Honestly, that kind of rigidity is probably the biggest liability a company can have today. Operational challenges are now defined by their volatility, their constant change. So if your organization can't rapidly test, validate, and then implement optimization strategies, you are almost by definition falling behind the curve. Simulation. It provides that necessary resilience. It directly addresses that fundamental instability we see everywhere. Really, it's the only practical way to model the hundreds, maybe thousands of intersecting variables. Machine uptime, operator speed differences, queuing theory effects, material availability fluctuations, all the things that make industrial decision-making so incredibly complex.
So the central question for you, our listener, as you're thinking through this is pretty simple, isn't it? When the future of your operational efficiency hinges on making the right organizational change, why would you rely on just an educated guess or maybe gut feeling? Why guess when you can actually rely on data-proven knowledge before you commit, before you implement anything?
No, before you go.
Exactly. So let's start with that core problem. The fundamental failure of the purely static approach to production. For decades, maybe generations, plant managers kind of operated under this assumption that, okay, once the line was laid out and the process was defined, that was it. It was fixed, set in stone. But, as you just pointed out, the second you face external pressures, maybe a sudden unexpected spike in customer orders, or a critical delay in your material supply chain, that fixed arrangement instantly becomes a bottleneck, a choke point.
It's practically a guaranteed path straight to inefficiency. Because fundamentally, that fixed setup is applying a rigid solution to what is inherently a fluid dynamic problem. Think about it. When your core operating parameters change, let's say customer demand shifts, meaning you suddenly need different processing times at different stations on the line, well, that original layout starts creating these hidden bottlenecks. Or maybe it generates excessive non-productive time. Sometimes these are called micro-stoppages, tiny little pauses that manual tracking or human observation simply can't catch. But they add up.
Right, those little 10-second delays here and there that nobody really notices until you look at the aggregate data.
Precisely. and they kill efficiency over time.
Okay, so this brings us naturally to the concept of testing variance. And we need to be clear here, this isn't just about tweaking a single machine setting by, 0.5%. We are talking about potentially profound operational shifts, the kind of changes that management teams typically view with, well, a lot of dread because of their disruptive potential.
It's exactly right. A variant in this context might involve something quite significant. For instance, completely changing the operation sequencing. Maybe your current process runs tasks A, then B, then C, then D. A variant could test running them in a new sequence, say C, then A, then D, then B, to see if material spends less time just sitting, waiting between steps. Or it might be a really radical adjustment to the load balance between shifts, determining if mathematically 2 longer, perhaps more focused shifts are actually superior to 3 shorter shifts, especially when you factor in the inherent inefficiencies of shift handoffs.
Those handoffs can be surprisingly costly in terms of lost time and potential errors.
They absolutely can. Or another variant could be a complete reconfiguration of the physical layout of workstations. Maybe moving things around to drastically reduce the internal transport distance for materials or people. These aren't trivial changes. These are potentially massive, high-stakes decisions for any operation.
Which is precisely where the genius of the simulation advantage comes in. Testing dry, as it's sometimes called, you move all that high-stake risk entirely out of the physical world and into a computational environment. You can crash the digital plant 1,000 times testing extreme scenarios. You can break the virtual machines. None of it impacts a single real-world delivery or costs you a penny in downtime.
And that capability, that freedom to experiment without consequence, it fundamentally elevates the entire level of decision-making within the company. We transition away from statements like, well, based on my 20 years of experience on this floor, I believe this new staffing level will probably save us some money. Instead, we move towards, okay, the digital twin simulation, which is being fed by real-time sensor data from our machines, demonstrates that this specific configuration achieves a 15% reduction in lead time while maintaining our target resource utilization above 90%.
It's a different world. That shift, though, from belief to actual proof, it absolutely requires measurable results. You need hard numbers. So can we elaborate a bit more on the critical key performance indicators, the KPIs, that these simulations allow companies to really benchmark across all those different variants they might be testing?
Absolutely. The source material we looked at really emphasizes 4 crucial factual outputs that simulations make directly comparable between scenarios. First, and perhaps most obviously, is the time of realization. Essentially, the overall lead time for an order or a product. And critically, this isn't just the theoretical processing time added up. No, it's the total time a work piece or an order spends within the entire system. That includes all the waiting time, all the transport time, modeled precisely for each specific variant you're testing.
So it captures the reality, not just the ideal plan?
Exactly. Second is resource utilization. Human intuition, even experienced intuition, often overestimates how busy machines or people actually are. Simulation, particularly when you're dealing with these complex, multivariable environments, it highlights exactly which machines or which personnel are genuinely maxed out, and crucially, which ones are sitting idle more often than you think. It measures not just machine availability as it turned on, but its actual productive use across a specific operational scenario. Big difference.
Okay, wait a second. If the simulation is going to be truly accurate, it must capture all that subtle, often overlooked, non-productive time, right? We often see the term prestoge in some of the Eastern European industrial texts. But here, we're just talking about downtime, but not just the big, catastrophic machine breakdowns. We mean everything.
That's absolutely right. The third key metric is that comprehensive level of downtime, or maybe better termed, non-productive time. And yes, we're talking about much more than just scheduled maintenance breaks. Simulations are so powerful because they reveal those hidden queuing delays. They uncover the microstoppages caused by maybe inefficient material flow paths between stations or bottlenecks that only arise because of unexpected variations in processing times that you wouldn't normally account for. The model quantifies the true cumulative cost of all these small pauses under each variant being tested.
And finally, the bottom line, translating all of that operational detail into actual money.
Yes. The fourth critical metric is operational costs. By linking resource utilization data, staffing requirements for each variant, and the total operational time simulated, the platform translates every mechanical or organizational change directly into its impact on the bottom line. For instance, if one layout variant requires, say, 10% less machine running time to achieve the same output volume, the cost saving in electricity and wear and tear, maybe even consumables, that becomes quantifiable immediately within the simulation results.
So let me get this straight. If I model 5 completely different ways to organize my welding station area, I don't just get 5 subjective opinions from different engineers. I actually get 5 distinct quantitative reports detailing the precise impact each option would have on my lead time, my resource use, my hidden downtimes, and my operating costs.
That's precisely it.
Wow. It essentially strips the ego and the guesswork right out of operational planning, doesn't it?
It really does. It forces teams, or at least encourages them strongly, to adopt a continuous improvement cycle that's based entirely on empirical evidence, on data. This capability, honestly, it's the foundation of modern, truly lean manufacturing. It gives companies the factual basis they need to
Yeah.
adapt to change without the paralyzing fear of getting it wrong.
Okay, this all sounds incredibly powerful, almost ideal, but we have to address the elephant in the room here. Data integrity. If the core argument, the whole value proposition, is that the simulation proves the optimal solution, then the data feeding that simulation absolutely must be utterly trustworthy.
Right.
Because garbage in, well, it leads to potentially catastrophic risk out if you implement a bad plan based on flawed data.
That is, without a doubt, the most crucial point in this entire discussion. A simulation is only as credible, only as reliable, as the fidelity of its input data. Full stop. If you are feeding the model numbers based on, 5-year-old efficiency reports gathering dust on a shelf, or maybe timings done manually with a stopwatch last quarter, your variant comparisons will be fatally flawed. And that could lead you to making a very high-cost implementation of what is actually a suboptimal plan a terrible outcome. Therefore, the absolute foundation for reliable simulation requires high fidelity, highly current data. We're talking accurate operation times, real machine efficiencies, genuine material flow rates measured automatically, and capturing those true downtimes, including the microstoppages. The rule here is absolute. The more current and the more precise the input data, the more reliable the conclusions you can draw from comparing different variants.
Okay, so this immediate dependency on precise, granular, real-time data, it leads us directly to the technology needed to actually gather it. I'm guessing a traditional ERP system, or maybe even a basic factory data acquisition system, probably isn't enough on its own to provide the level of detail needed for a really high-fidelity digital twin, is it?
And that's exactly where a platform like DBR77 really makes its entrance. GBR77 was essentially developed specifically because the market generally lacked these kinds of integrated solutions capable of providing this necessary level of analytical precision and automation. It's designed from the ground up to be a comprehensive digital transformation platform, integrating all the necessary components seamlessly together.
What are those necessary components then? It sounds like DBR77 is actually much more than just a simulation software package.
Oh, it is. It's conceived as a complete ecosystem. It integrates 4 core technological pillars. First, the Internet of Things, or IoT, for the crucial data collection piece. Second, the digital twin itself for the modeling and simulation. Third, artificial intelligence, AI, for adding predictive analysis capabilities. And fourth, even a smart marketplace component for optimizing resource allocation. But focusing specifically on the simulation aspect, that critical data collection component is primarily handled by the DBR77 IoT solution.
Okay, let's dive into that IoT solution a bit more. When we talk about these advanced systems using dedicated sensors, what exact data are they capturing that makes the simulation input so much superior to, say, traditional manual methods or older systems? Give us the details our listener needs here.
Right. So the DBR77 IoT solution goes far, far beyond just capturing a simple on-off status for a machine. That's basic. It utilizes dedicated sensors, sometimes retrofitted, sometimes built-in, that monitor dozens of machine parameters continuously in real time. Things like motor load, very specific energy consumption signatures that can indicate tool wear, vibration data, temperature fluctuations at critical points, and perhaps most importantly for simulation accuracy, precise cycle times measured down to the millisecond. This level of granularity allows the system to accurately identify and measure those elusive microstoppages we talked about. Those quick, maybe 10-second pauses between cycles that, over a full shift, might easily aggregate to 30 minutes or more of lost production time, but are completely invisible to human observers or standard reporting.
Ah, okay. So the digital twin isn't running its simulations based on the theoretical maximum speed of Machine X listed in the manual. It's running simulations based on the actual current high-fidelity performance of Machine X right now, factoring in its real-world vibration data from this morning and the actual load it experienced during the last shift. That's the critical link between the virtual and the physical.
Exactly. That's the core of the fidelity. And this high-fidelity input doesn't just ensure that your current operational analysis is accurate. It also enables really robust future-proofing capabilities.
Hmm.
Companies can take this precise current operational data and combine it within the simulation environment with forecasted data. Things like projected demand growth figures from sales, maybe anticipated material cost volatility from procurement, or even known upcoming major machine maintenance schedules from the maintenance team. You feed all that in to build incredibly detailed future-oriented scenarios.
Wow, okay. So that really turns the simulation from just an optimization tool for today into a powerful strategic foresight tool for tomorrow. You can actually ask the system things like, okay, if our market forecast shows demand increasing by 25% over the next 2 quarters, and we know we're going to lose two key experienced operators to retirement in that time frame, which of these five potential new layout variants ensures we can maintain profitability and still meet our customer lead time guarantees?
You are essentially modeling disruption before it happens. You're testing your resilience digitally. So instead of being purely reactive when things change, companies can use a platform like DBR77 to proactively build and test variants that specifically mitigate projected challenges months or even a year ahead of time. This ensures they have the infrastructure plans, the operational plans already validated and ready to go when those future events actually occur. It's about proactive adaptation.
Right. We've firmly established the crucial need for accurate real-time data as the foundation. Now, let's explore the computational powerhouse that actually takes all this rich data and runs those complex scenarios. The DBR77 digital twin technology. You mentioned it's the central pillar of their offering. Now, lots of people use the term digital twin somewhat loosely these days. What exactly is the DBR77 definition of this tool? How do they conceptualize it?
That's a great point. The term is used broadly. Within the DBR77 context, the digital twin is defined quite specifically. It's conceived as a virtual and mathematical model of the actual physical plant, or maybe a specific production line, or even a logistics center. And it's absolutely crucial to understand that it's far more than just a fancy 3D visualization, although that's often part of the interface. The visualization is just how you interact with it. The real power lies deep within its computational backbone. This typically uses advanced simulation methodologies, most commonly discrete event simulation, or DES, sometimes coupled with agent-based modeling for capturing complex human or autonomous system interactions.
Got it. So it's not just a digital blueprint or a static diagram. It's more like a living, dynamic equation of the factory floor. An equation where every significant interaction, every machine cycle time variation, every material buffer level change, maybe even probabilistic models of operator decisions, is assigned parameters derived directly from that real-time IoT data feed.
Precisely. That's the core concept. And this means that when the platform tests a particular variant, it's not just doing simple calculations. It's actually running hundreds, maybe thousands of simulated cycles. It does this based on those probabilistic distributions of machine speeds, potential downtimes, operator efficiencies, and so on that reflect reality. It calculates the complex queuing effects where things get backed up, and even potential collision probabilities in automated environments, things that are absolutely impossible to predict accurately using just human intuition or simple linear math on a spreadsheet.
Okay, let's detail the mechanics a bit more then. How does a user, say a process engineer or a plant manager, actually interact with this digital replica to define and then test these different production variants? What's the workflow like?
The process is generally quite structured to ensure reliable results. First, the users define the specific scenario parameters they actually want to test. This could involve changing the core production parameters, maybe increasing the target output for the line by 15%, for example. Or it could involve defining organizational changes, like adjusting the number of work shifts from 3 down to 2, or maybe reducing the allowed inventory buffer size at a specific bottleneck station. Importantly, users can often also physically redesign the model within the interface. They can propose new physical layouts, maybe drag and drop workstations to new locations, or reroute the virtual material pathways within the twin environment itself.
Okay, so they define the what-ifs, and once those variants, those different potential futures are defined and input into the system, the platform then runs the heavy computational analysis.
Yes, exactly. The DBR77 digital twin then executes a simulation, runs for each of the proposed variants, often doing this concurrently to save time. And the direct output is that crucial comparative analysis focusing on those 4 key KPIs we discussed earlier: lead time, resource utilization, the level of downtime and productive time, and overall operational cost. The analysis can typically be run in 2 main modes, either analyzing current conditions using live data for immediate operational fixes finding today's bottleneck, or utilizing that predictive forecasting data we mentioned to test the viability of changes 6, 12, or even 18 months out.
What really stands out to me here is the flexibility and the scope of the analysis. I can imagine a CEO wanting to optimize the entire factory hall's flow, looking at the big picture, but a process engineer might only care about optimizing one specific troublesome production line that's always causing delays.
And that granularity is absolutely key to its practical utility. DVR77 allows the scope of the simulation and analysis to be precisely defined by the user. So yes, comparisons can be made across the entire facility, looking at the macro flow of all materials and final goods from receiving to shipping. Or they can be intensely focused specifically on solving a persistent bottleneck within one particular production line. Or you could even drill down further, maybe analyzing just a single isolated process, perhaps optimizing the complex relationship between two cooperative robotic arms and their shared human supervisor.
That level of detail is impressive.
And if we connect this back to the bigger picture, the digital twin really functions as the central nervous system of the entire DBR77 ecosystem. By providing this virtual yet high-fidelity testing ground, it directly fulfills that broader mission of achieving much higher operational transparency and truly integrated intelligence across the business. It's the component that transforms all that raw sensor data from the IoT devices into actionable strategic knowledge. It allows a company to pivot quickly, to minimize non-productive time and optimize flow across their entire value chain, not just in isolated pockets.
Right. Let's pivot ourselves now, moving from the technology and the theory behind it to the actual tangible gain. Industrial leaders, plant managers, CEOs, they need concrete evidence. What really happens when companies systematically embrace testing variants using this type of sophisticated digital twin technology? We need to bring these benefits to life with some specific, maybe even anecdotal examples from the sources.
Absolutely. The case studies are where the value becomes undeniable. They demonstrate that the benefits aren't just theoretical. They are often immediate and quite substantial. Let's look at that sporting goods manufacturer that was mentioned in the source material we reviewed. They were apparently struggling with consistently long lead times for a key product line. Their management team had, I believe, 4 competing ideas internally for a new station layout design. Now imagine trying to physically implement and test all 4 of those layouts in the real factory. It would have been chaos, probably cost millions, and disrupted production for weeks, if not months.
Total non-starter in reality. So what did the digital twin reveal when they modeled those 4 options?
They modeled all 4 layout variants within the DBR77 twin environment. The simulation meticulously analyzed how each proposed layout, which involved physically repositioning cutting tables, assembly stations, and material racks in the virtual model, affected things like material queue lengths at each stage, operator travel paths between tasks, and critically, how the resource utilization levels reacted under simulated demand spikes, which is a key issue for them. The result: the selected optimal variant, the one the simulation proved was best, wasn't necessarily one that management had initially favored based on intuition, but the data was clear. It shortened the overall production time for that product line by a very significant 15%.
Wow, 15%.
15%. And this was achieved not through buying new, faster machines or hiring more people, but purely through organizational intelligence, reconfiguring the flow based on simulation proof before touching anything physical.
That is a massive gain. A 15% improvement on flow time, just from changing the organizational structure, validated first in a virtual environment. That's compelling. Let's look at another common scenario. Decisions around shift changes and controlling operational costs. This is something managers wrestle with constantly.
Definitely. Consider the metal processing plant example. They were under pressure to reduce their operational costs, but obviously they were deeply concerned about maintaining their required production volume. They couldn't afford a drop. So they used simulation to compare 2 core scenarios. First, their existing 3-shift operation, which they knew involved higher overall labor costs, and also suffered from some fatigue-related downtime toward the end of shifts and during handovers. The alternative they modeled was a proposed 2-shift model. This would require more focused, perhaps longer, work periods per shift, but potentially offered significant savings. The simulation allowed them to precisely map out the projected energy consumption under both models, calculate the exact labor cost differentials including overtime implications, and even estimate the predicted impact on machine wear and tear rates under the different utilization patterns. The analysis ultimately confirmed that they could transition safely to the 2-shift model. They could significantly reduce their operational overhead, their costs, without sacrificing the necessary production volume targets. They essentially replaced a costly, assumption-based structure with a data-validated, optimized operational model.
And it's not just manufacturing, right? These principles apply just as strongly to logistics operations. Packaging accuracy and error reduction is a huge area, especially for anyone in e-commerce or consumer goods fulfillment.
Absolutely critical. There was a logistics firm example as well. They utilized the simulation capabilities of their digital twin specifically to optimize their packing station sequences. They had a hunch, based on error reports, that the current sequence, the specific order in which items were scanned, labeled, wrapped, and boxed, was creating unnecessary operator movement and likely increasing the probability of human error, especially during peak volume periods like holidays. So by modeling 3 different packing sequence variants in the simulation, analyzing the simulated operator movements, task times, and potential confusion points, the simulation identified a specific flow that minimized the number of handoffs between steps and maximized clear visual confirmation points for the operators. The result, after they implemented the simulation-proven sequence, they managed to reduce their overall packing errors by a remarkable 40%.
40%, that's huge.
Huge. Think about the impact that has on reducing costly returns, protecting brand reputation, and lowering future logistics costs associated with fixing mistakes. Immense value.
These examples really underscore the powerful strategic benefits that go beyond just tweaking a process here or there. This isn't just about quick fixes. It seems to be about fundamentally building operational resilience and adaptability into the business.
That's exactly it. It allows for continuous, rapid adaptation to either internal changes, like new equipment, or external pressures, like shifting orders or supply issues. And perhaps most importantly, as we discussed, it effectively eliminates the need for those incredibly costly, high-risk, blind implementation decisions where you're just hoping for the best. Companies using this systematically can now regularly optimize their production processes, their layouts, their staffing models, without causing major physical disruption. And the cumulative effect we see is consistently better overall equipment effectiveness, or OEE, results. Significantly lower operational costs over time, much greater production flexibility to handle unexpected changes, and ultimately higher customer satisfaction because deliveries become faster and much more predictable. That predictability alone is often a major competitive advantage.
Okay, so for our listener who's now seeing the frankly undeniable value of using something like DBR77's digital twin for testing these production variants, they probably need a clear plan of action, a roadmap. Let's try to outline the practical steps, the necessary stages for a company to really adopt and systematically leverage this capability. Based on the sources, it seems like there are about essential steps for achieving success here.
Yes, a structured approach is definitely recommended. And step 1 is absolutely crucial, clearly defining the core problem or the challenge you're trying to address. You must articulate, in measurable terms, the specific inefficiency you're trying to solve. Is it unacceptably high inventory carrying costs? Is it excessively long lead times for one particular key product line? Or perhaps it's persistently poor resource utilization at a critical expensive workstation. You need that clear target.
Makes sense. Define the mission first. Once that mission is clear, step 2 seems to be creating the baseline process model. This is where the digital twin of the current state is actually built and then populated with that high-fidelity, real-time data coming from the DBR77 IoT solution we talked about. This accurate model of how things are right now serves as the indispensable control group, the benchmark against which all your proposed variants will be measured later.
Precisely. Then comes step 3, the innovation or design phase. This is where you actually design the alternative variants you want to test. And this really should be a collaborative effort. It's not just one engineer in a dark room. It should involve brainstorming and iterating on possibilities, maybe testing different machine routings, experimenting with changes in inventory buffer sizes between stations, or perhaps modeling radically different team assignments or skill mixes. Get operational input here.
Right, get the people who do the work involved in suggesting improvements. Then, step 4 is the execution phase, actually running the simulation. This is where the computational power of the digital twin takes over. It systematically tests all those defined variants against the baseline model, running thousands of simulated cycles, and it generates those comprehensive KPI comparison reports we discussed: time, utilization, downtime, cost. This data then makes the subsequent selection decision objective, not subjective.
Correct. Which leads directly to step 5. Selecting the mathematically superior solution, the winning variant, based on that hard data, and then meticulously preparing for its physical implementation on the shop floor or in the warehouse. Notice how the effort shifts here. It's less about agonizing over what to do. The simulation answered that, and more about focusing on how to execute that chosen change efficiently and smoothly, because the major risks have already been managed and quantified in the digital realm.
And finally, the cycle doesn't just end with implementation. Step 6 is critical: post-implementation monitoring and ongoing refinement. Once the optimized plan is live in the physical world, the IoT system continues to track the actual performance. You compare that real-world data back to the simulation's original predictions. Did reality match the model? This verification step allows for minor tweaks and adjustments if needed, and perhaps more importantly, it embeds that continuous improvement cycle as a standard operational mindset within the organization. It becomes the new way of working.
That six-step framework seems robust, and it is when implemented well. However, we absolutely must not ignore the real-world hurdles and challenges involved in adopting and effectively using such advanced technology. Critical thinking demands we address those potential pitfalls.
Absolutely. What are some of the common roadblocks or pitfalls that companies tend to face when they try to implement systematic variant testing using digital twins? I have to imagine data quality remains a persistent struggle, even with sophisticated integrated systems like DBR77.
It absolutely does. That need for current, reliable, high-fidelity input data is relentless. It never goes away. Companies often underestimate the ongoing effort required for data governance, ensuring the quality and accuracy of that IoT feed over time, especially as new machines are inevitably introduced onto the line, or processes get slightly altered in minor ways. If data reliability starts to wane, even slightly, management risks losing faith in the entire simulation model's outputs, which can derail the whole initiative. Maintaining data trust is paramount. Another very significant hurdle is often organizational and, frankly, cultural buy-in. Implementing a digital twin and simulation strategy cannot just be an isolated IT project run by engineers. You absolutely must involve the operational teams, the machine operators, the line supervisors, the maintenance crews deeply in the design of the variants being tested. Why? Because if the proposed changes, which might look mathematically optimal in the simulation, aren't grounded in their practical day-to-day knowledge of material handling nuances or safety constraints or ergonomic realities, then those variants, while looking great on screen, may turn out to be physically unfeasible or even unsafe to implement.
That makes perfect sense. You need that reality check from the floor. And I suppose modeling human variability, things like differences in operator skill level, learning curves, or fatigue effects over a long shift, must be far more complex than modeling purely deterministic machine throughput rates.
It is inherently more complex.
Yeah.
And that points to another challenge: the sheer difficulty in accurately modeling extremely complex, often nonlinear processes without highly sophisticated simulation tools. Simpler simulation software packages often fail to adequately account for the stochastic or random nature of many industrial processes, unexpected breakdowns, quality variations, etc. This can lead to overly optimistic or simply inaccurate results. The complexity of accurately modeling things like queuing effects across dozens of interconnected machines with shared resources like operators or transport systems really does require a robust industrial-grade platform like DBR77 that's built for this purpose.
And finally, even with high-fidelity data and a sophisticated model, there's still that crucial accountability check, right? You still need human oversight and validation.
Indeed. The final crucial requirement, and a potential pitfall if ignored, is the absolute necessity to verify the simulation results using personnel who possess deep, practical, hands-on operational experience. These experienced folks provide the ultimate sanity check. They need to review the simulation outputs and question whether the data-driven optimization actually aligns with the physical reality they know intimately. Does it feel right based on their years on the floor? This layer of human validation is critical. It prevents a kind of blind adherence to a model that, despite its mathematical precision, might have inadvertently overlooked some crucial, perhaps non-quantifiable factor present in the real operating environment.
Okay, so let's try to synthesize all of this. What does this all mean at the end of the day? Our deep dive today has, I think, really illuminated how modern industrial platforms, and specifically DBR77 leveraging its powerful digital twin technology, are fundamentally transforming operational strategy. They are turning production planning away from being a high-risk gamble, often based on historical precedent or individual intuition, and turning it into a highly precise, data-driven, scientific process. Simulation, used this way, really becomes the bedrock foundation of systematic optimization. It allows companies to continuously adapt, iterate, and improve their efficiency, driving down costs and drastically enhancing customer reliability through predictability.
You could almost say it allows you to run decades of potential operational failure scenarios in maybe just a week of simulation time. You learn the optimal path digitally through experimentation, and then you implement it physically only once, and you do it with a high degree of confidence. It's arguably the ultimate application of sophisticated risk management principles directly to the heart of operational planning.
And by testing dozens, maybe hundreds of different configurations in that safe digital space first, you ensure that your capital, your valuable engineering effort, and your management attention are focused only on implementing those solutions that have been mathematically proven to maximize performance against your specific goals.
Which leaves us, perhaps, with a final provocative thought for you, our listener, to consider as you reflect on this. Given that we've seen high-fidelity simulation allows for the detailed testing of highly complex scenarios, everything from subtle shift pattern changes right up to entire factory floor redesigns before spending any physical capital or disrupting operations, how much systemic value and how much measurable, tangible cost saving is potentially being lost every single day by companies all around the world that are still primarily relying on those traditional, disruptive, often incredibly costly physical trial and error methods within their actual running plants? How much waste is built into the old way of doing things?